Welcome to the lecture on Earth structure and motion. This is being recorded on, what is today? February 5th, 2013. But considering how long the solar system's been around, I don't think things will change much by the time you listen to this. Also, I have a slight cold, so if I don't pronounce things well, one, that's normal, as you know by now, and two, that's a possible explanation. Here are some of the objectives. I'm not going to go through these because they are listed in the first section of every topic. But look at these. If there are any objectives that I included in the test that weren't here, let me know. And if there were some that were here that weren't in the test, let me know, because it's good to match everything. These are the words that we're going to be covering today. Again, these are in the first section of every topic. Earth shape. When we talk about Earth shape, this is what we tend to think about. A ball or a sphere. Kinda. It's not quite. Now, there's a lot of evidence that we knew that the Earth was sphere-like. It's really an oblate spheroid, and I'll talk to you about that in a while. But this never happened. We are taught that we were once taught that people thought the Earth was flat. I'm not convinced that was ever the case. I think that's the case in the minds of school teachers who didn't think very much. But there's a lot of evidence that the Earth was not flat. Again, this didn't happen. Where would the water go? People knew better. They didn't know what was over the edge. Every time there is a lunar eclipse, this happens. The shape of Earth's shadow on the surface of the moon is, well, round. This could happen if the Earth were in the shape of a quarter, a nickel, or a dime, but not every single time. The ancients knew this. People writing textbooks didn't. Kind of weird. We got stupid in between. Here's some more evidence. Alexandria of Syene, 200 and something BC to 190 something BC, was from Libyan Africa, but he did an experiment. He noticed there were two wells that were really deep, one in Alexandria, one in Syene, almost directly north and south of each other. On a flat Earth, if the Earth were completely flat and the sun were 93 million miles out here, the sun would make the same kind of shadow in each well. But what he noticed was that in Syene, which was exactly on the Tropic of Cancer, 23.5 degrees north of the equator, on the longest day of the year, in the northern hemisphere, the Tropic of Cancer, there was no shadow. In Alexandria, there was a shadow, something like 7.2 degrees. Well, if you count how many times 7.2 degrees goes into a circle, and then you multiply that by the distance between these two things, you can get the distance around the Earth. So, over 2,200 years ago, a guy figured out not only that the Earth was round, but how round it was. If we use the popular, or the different version of what's called a stadium, the unit he used to measure the distance, he was off by only 2%. Pretty incredible considering what he did. Also, we didn't know about all these time zones, but even in the Mediterranean area, they knew that the sun was not overhead at the same time in all places. That couldn't happen on a flat Earth. That would happen only if you have a curved Earth. Also, when you look up at the sky at night, all places don't see the same star overhead at the same time. That's essentially the same thing as time zones. I just like these pictures. They're kind of cool. Again, I have no idea where the water is going or where the replacement water comes from. Another thing, there is a horizon. On a flat planet, there really wouldn't be a horizon. You would just see into the distance, and the higher you go, well, you'd see essentially the same thing. But on a curved Earth, the higher you go, the further away the horizon is. If you're 6 feet tall, taller than me, you should be on the Suns because they need some basketball players. And two, you can see about 3 miles away to the horizon. If you're 2 meters tall, it's about 5 kilometers away if you want to go metric. And then there's the formula. You can calculate that out if you want. This is something else that was really obvious since we've had eyes. What do you notice about the horizon here? It's curved. I used to live on a little island in the South Pacific, an island of Tutuila. Went up to the highest point, 2,100 feet high. My students asked me why, but I did it. And when you looked out, you could definitely see the curvature of the Earth. It's not very much, but it's noticeable. Also, when a ship goes over the horizon, the last thing that you see is the top of the mast. That wouldn't happen on a flat Earth. The ship would simply get smaller and smaller and smaller as it goes into the distance. Another thought. Your weight is caused by gravity. In this case, you'd be close to the center of the Earth in the center of this flat section here. You would weigh, excuse me, a little bit more. As you go out to the corner, you'd be further from the center of the Earth and you would weigh a little bit less. Guess what? That doesn't happen. We weigh about the same thing no matter where we go on Earth, indicating the Earth has to be a sphere. Okay, this is the Earth's real shape. It is a tennis ball, and the word pin is written on the... Okay, maybe not. But if you've ever seen a tennis ball or a racquetball spinning rapidly, you know that it gets fat, what we call oblate. Earth is kind of like that. When it was forming, and even now it is spinning, and that throws part of its mass out toward the equator. It's a little bit shorter pole to pole, a little bit further across the belt line. Here you go. 12,714 kilometers, pole to pole, 12,756 across the belt. A little bit further this direction, which means if you take something that weighs 194 newtons at the pole and move it to the equator, it's so much further away. Whoops, sorry, 195. And move it to the equator, it becomes 1 newton less in weight. It doesn't lose any mass. It simply loses weight, or the attraction, between it and the mass of the Earth. If you move it way out into space, the further you move, the less weight it has, but again, the mass stays the same. There is modern evidence for all this too. Go up in an airplane, you can see the curvature. Astronauts have taken pictures. And when you look at it in space, everything else, for the most part, all planetary type things, are spherical. Now, how much is water and how much is Earth? Roughly this. 70 and 30, or 71 and 29 if you want to be a little bit more exact. It really is a big blue marble in space, as Carl Sagan said. It is mostly water. And as we melt this stuff, it becomes even mostly more water. By the way, news today, the Iditarod dog race, for the first time in recent history, actually maybe any history, they had to cancel the race. Excuse me, there's not enough snow. Layers of the Earth. Despite what your middle school teacher might have taught you, geophysicists break the Earth into 4 principal layers. The Earth itself. We have the crust, which is incredibly thin. We have the mantle, which is the major part of the Earth. We have the outer core and the inner core. We live on the crust. The mantle goes from being fairly solid near the surface to very fluid or plastic-like underneath here. The outer core is molten and it's flowing, and this is what leads to our magnetic field, the movement of hot molten iron and nickel. And yet the solid core is under so much pressure that it is squished back into a solid even though it is hotter. Now, there are a couple of different ways to look at this. Since the upper part of the mantle and the crust tend to act as a unit, we call them the lithosphere, or the rock sphere. And those parts tend to move around together in plate tectonics. The lower part of the mantle becomes a little bit more plastic, and the lower part of the upper mantle, I guess I should say, becomes a little more plastic, and that's called the asthenosphere. Here you go, and again, this crust is way too thick in this drawing. Our highest mountain, Mount Everest, 5 miles high. Our deepest trench, Marianas Trench, about 5 miles deep. 10 total miles out of 4,000 all the way to the surface. It would be thinner than a pencil line if we were drawing this accurately. The denser stuff goes to the middle, just like you put dense stuff in the swimming pool. It goes to the bottom. The styrofoam and the air float things go to the top. There's a reason the continents are on the surface. Excuse me, they are the less dense rock. They float up there. When are these things going to sink to the bottom? Well, they're not. When is a piece of styrofoam going to sink to the bottom of your pool? It won't. It's less dense. Here is a nice little summary from a college site. It is a little distended, I'll grant you. But this is good to look over. Notice the major mass of the Earth is in the mantle. The crust is way too thick in this drawing. It should be thinner than that line. And the crust, by the way, is thickest under the mountains and thinnest under the trenches in the ocean. I know it's kind of weird, but the depth of the crust is mirrored by the height of the mountains. You have a high mountain, deep crust underneath. It's like a boat. You pile a lot of stuff into a boat and stack it really high, the boat itself goes deeper in the water. Here's the summary from your book. Inside to outside, inner core, solid, outer core, liquid, mantle, solid, but it flows, and the crust is solid. Now, where is north? Well, that's kind of a weird question. It depends on which north you're talking about. If you're talking about the North Pole of the Earth, it's where, if you ran a broomstick through the Earth from the South Pole to the North Pole and kept it going, I don't know, 620 light years, say, you would almost run into the star Polaris. Polaris, the North Star. But when we use magnetic compasses, that's not the same north we're using. If you're in Earth Science 1, you'll recall this, because magnetic north is completely different from geographic north. Here's geographic north. Here's the path of magnetic north. Long time ago in the 1600s, Magellan time, that's where your compasses would point. When you guys were born, ooh, it was somewhere in here. Right now, it is somewhere up here. For a long time, it hung around this island called Elefregnos. But it's migrating, again because the flowing of the liquid iron and nickel in the Earth's outer core. Now, why is Earth hot? 1, we have some original heat left over from about 4.5 billion years ago. Things don't cool off quickly in a vacuum. 2, there's a lot of pressure. Whoops. You put all those miles of rock on top of you, you'd feel the pressure. And that pressure results in greater collisions between the particles. The greater collisions between the particles result in greater heat. And the third, and the biggest one, is there are radioactive materials. Thorium, radium, uranium inside the Earth. They're very dense. They've sunk down there. And as they decay, they release heat. Now the Earth cools to about 70 meters. If you've ever been down into a cave, up to about 220 feet, it cools off. And then it starts warming. About 1 degree Celsius for every 40 meters, but that happens only for the first 1,000 meters. I used to take my students on field trips to Carlsbad Caverns. We went in Carlsbad Caverns, and for the first little while it was kind of cool, and then it begins to heat up. We went into a tour of caverns under the caverns, and it was so warm, nobody needed jackets. How warm does it get? The deepest mine in the world, the working mine, is about 12,800 feet, 2.5 miles deep. The rock down there is 140 degrees Fahrenheit. They have to air condition the mine in order for people to work down there. What if there were no heat on Earth? What if there were no radioactive materials decaying? You wouldn't have the heat rising. You wouldn't have the mantle flowing. We wouldn't have plate tectonics. We wouldn't have mountains. With the water and the atmosphere on the Earth, everything eventually would be worn down, and there'd be enough water to cover all the land about 1 mile deep. But that's not the way it is. We're going to pause there. I'll see you in part 2.